Okay, let's talk about heap data structure. And before that, let us try to understand an application of a priority queue. Say you're a doctor and there are patients in the waiting room, and each of them has a priority associated with them according to their level of injury or how sick they are, and so on. So each of them have priority attached to them, and depending on this priority, we want to process the patients or treat the patients according to their priorities. So that is, we want to treat the patient with the highest priority first, and then the next highest priority, and so on. So another common application of a priority queue would be that of a CPU is deciding to pick which task it must execute, and according to the priority associated with that task. So that those are some very common everyday applications of a priority queue. And okay, so hang on. I was talking about heap, and then I also introduced this notion of priority queue. Are they the same? Well, the answer to that is no. A priority queue is basically an abstract data type, while a heap is basically a data structure. An abstract data type would be something like a stack or a queue. Let's consider a stack. It's abstract because we do not really care about how the stack is implemented, but we are only interested in the functionalities that is exposed by the stack. So, for example, we want the stack to obey the last in first out property. So, we would only care about the push and pop operations, where you push items onto the stack, and you are interested in popping the recently inserted items. So that is all we care about, and we do not really bother about the implementation details. That is an example of an abstract data type. So you can even implement an abstract data type using another abstract data type. For example, a stack can be implemented using queues. So and so on. So we are really not bothered about that, and we only care about the functionalities exposed by the data type. So a heap is not a priority queue, but it's actually one of the ways to efficiently implement a priority queue. There may be many ways to implement a priority queue. So while it is possible to implement a priority queue using another data structure, uh, it may or may not be as efficient as a heap, because a heap is able to insert an element into the priority queue, delete the top element, and also able to fetch the top element efficiently, and it serves the purpose of a priority queue. So, so I hope the distinction between a priority queue and a heap is clear. So let's define a heap formally. A heap, more specifically a binary heap, since we are dealing with only two nodes here. So is a special kind of a binary tree, that is, it's a complete binary tree. A complete binary tree is a binary tree with nodes filled up completely in all the levels except possibly the last level. And also, the second property that it needs to obey is that the value of each node is greater than or equal to the values of the left and right child. And this second property is defined according to whether it's a max heap. In that case, we need the values to be greater than or equal to. If it's a min heap, then the same property is modified to be the value of each node is less than or equal to the values of the child nodes. So these are the two properties, and if a binary tree obeys these two properties, then it becomes a binary heap. So just to make things clear, let's have a look at different binary trees, and we just figure out if they're complete or not. So the ones at 1 and 2, they are complete because they're filled up. One is basically filled completely in all the levels. The second one, it is filled completely in all the levels, and except the last one. And in that case, note that we are filling it starting from the leftwards, like we're filling it leftwards, and that isn't true in the third tree, where in the last level the leftmost node is missing. So we don't want that. Like a binary tree is a complete binary tree only if it either has nodes in all the levels, or in the if it is like not completely filled, it has to be in the last level. And even in that case, we want it to be filled leftwards. We don't want like any variation like the third. So I hope that is clear. And like I already mentioned, we have two kinds of heaps. We have a min heap and a max heap. Min heap is basically where the value of the node is basically less than or equal to uh, the child nodes. So as you can see, 1 is less than or equal to 2 and 3, and again 2 is less than or equal to 6 and 4. 3 is less than or equal to 5. And in the case of a max heap, it's just the other way around, where 6 is basically greater than or equal to 5 and 4. 5 is greater than or equal to 1 and 2, and 4 is greater than or equal to 3. So in the min heap, the top element is basically at the root node, and this will be the minimum element, the minimum valued element among all nodes. And in max heap, again, like the maximum node is going to be at the root of the tree, and this is 6 in this case. And note that we can get both these values in order one time, and that is exactly what we want to do with a priority queue. So here comes the question: how do we store our heap in memory? Well, there's a general trick of converting a tree into a linear array. And this very trick is used in several other tree related problems. And it's also used while implementing segment trees. And a very similar trick is also used in Fenwick trees or binary index trees, but that would involve some bit manipulation or binary magic to get the left left child or the right child of a node and so on. But the general idea remains the same. So the trick goes as follows. So we basically just store the tree level wise in the array. For example, like we have 6, 5, 4, 1, 2, 3. So I'm storing 6, then I'll store 5, 4, and 1, 2, and 3. So I'm sort of filling the array level wise, and we would also want to be able to access the parent of a node, and at the same time the left and right child of a node. And how do we do that when we are storing that as an array? So the trick would be to just sort of remember these rules, although they do make perfect sense. So if you just think about it, it does make sense why we'll be using this to get the parent of an index I. So let's say we want to get the parent of 3, and 3 is basically stored at index 6. So how do I get the parent of 6? So I just do 6 divided by 2, and that would be 3. And so I just jump to index 3, and there you go. I have the node 4 as my parent of 3. So that's the idea. So uh, the floor value of I by 2 is going to get the parent of I. So know that we are dealing with indexes here, and you'll have to access the array to get the exact value. Similarly, the left child of an index I, a node index I, is going to be given by 2 times of I, and the right child of an index I is going to be stored at index 2I plus 1. So, for example, if I take 5, 5 has an index 2. I basically start filling it from index 1 instead of index 0. Note that I do not have anything at index 0. So that I can ensure these rules work, and I can get the parent nodes and the children on the fly. And it just makes life easier rather than having to just fill it from index 0, in which case the rules will differ. So there you have it. Like if I have 5, which is stored at index 2, I get the children of 5 simply by going to 2 into 2, which is 4. And so I have 1, and then 2 into 2 plus 1, which is 5. So there you go. At index 4 and 5, I basically have the children of 5. And so that's pretty much how I actually like get the parent nodes as well as the children on the fly. And there you have it. So that's the trick we use to basically store our heap in memory in the form of a linear array, and just get comfortable with this idea, because we'll be using that a lot to actually implement our heap operations. And we'll discuss about that in the next part. So that's it for part one.